Hello, everybody. Our speaker today is Anton Galaev, one of the organizer of the seminar. So he shall give a talk on holonomy of K-contact, sub-Riemannian manifolds. Please, Anton.
Yes, thank you very much, Pan, for the introduction and for the possibility to give this talk. In fact, almost the same talk I had in Brno in September at DJ conference. There was some development, but still new results are not published, so I will not speak about them. At the end, I will just announce them. So as the title suggests, we'll speak about holonomy groups of K-contact sub-Riemannian manifolds. So I will explain these results. Results that I will discuss are now published in this paper with the same title as the talk. Now, for motivation, just for motivation, let me recall standard situation when we have some connection nabla on the tangent bundle, and then we have notion of parallel transport whenever we have curve gamma, a piecewise curve gamma in M, then we obtain map, which is called parallel transport from the tangent space at the starting point to the tangent space at the end point. In fact, when we have a single vector at the point gamma A, then there is a unique vector field called parallel vector field along, just defined along the curve, and the result of the parallel transport is the value of this vector field at the end point. So when we consider loop, a closed curve at the point x, then the end point is the same, and the vectors that we obtain belongs to the same tangent space. So we get, because this is done for arbitrary vector x0, we get transformation of the tangent space in the holonomy group of this connection nabla consists of all such transformations. It's necessary to consider all possible curves, loops, or possible loops at the point x and corresponding parallel transports. Now, important classical result is a classification of Riemannian holonomy groups. If a group is irreducible, then and connected, then it belongs to that list. And additionally, there is a list of holonomy groups of Riemannian symmetric spaces, and those spaces are known. And in particular, when we have simply connected a Riemannian manifold with a parallel spinor, so this is spin structure and parallel spin, then there exists parallel spinor if and only if holonomy group is one of those four. Generally, manifold may be product of other manifolds with irreducible holonomy, and some holonomy just product of those groups in this list. Now consider the following situation. Suppose that we have manifold M and we have some distribution D on the manifold M. For the moment, arbitrary distribution, smooth distribution. Then a horizontal connection on the distribution D is such covariant derivative. So we see that we may consider covariant derivative of sections of D in direction, only in the direction of sections of D. Generalization of usual connection. Now we may consider curves or vectors tangent to D. Such curves, vectors are called horizontal. And such connection also define parallel transport, but it is defined only along horizontal curves, and it transports the vectors tangent to D. So such parallel transport, this is a horizontal connection, then it is clear we may define holonomy group. Also for such connection, we should consider some point and consider all possible horizontal loops at that point and corresponding parallel transports. Next, let me consider a sub-Riemannian space. So suppose that we have this distribution D still at the moment arbitrary distribution, and some metric G defined only on the fibers of D, so sub-Riemannian metric, and fix some region, some additional distribution, such that we have such orthogonal decomposition of the tangent bundle. Pi prime would be projections. Then there is a so-called Schouten connection. So Schouten connection, it is similar to the Levi-Civita connection. It is given by such Cauchy type formula. The difference with the Levi-Civita connection is that we don't know if D is integrable. So it's necessary to consider in these terms projection to D. And in particular, this is unique connection satisfying those two properties. G is parallel with respect to nabla. So it means that when we consider parallel transports along horizontal curves, then metric is preserved. G is defined only on D. And such torsionless condition, but again with the projection pi. It's not quite usual torsion. So this was introduced by Schouten. Next, Schouten-Cauchy of this connection is defined similarly to the Riemannian Cauchy, but it is here we have again projection pi, and other additionally we have this term. Otherwise, it's not tensor field without this term. This tensor field, Schouten-Cauchy, it satisfies behind identity with zero right hand part, but it doesn't satisfy some properties of the usual Cauchy tensor. In particular, generally, it is not true. It is not true that connection is flat if and only if R is zero. This is not true. And next notion of extended connection. So we have some horizontal connection, then extended connection is a connection already in the vector bundle D. We are allowed to consider covariant derivative in arbitrary direction, but when we restrict it to D, it is just the initial horizontal connection. Of course, such extended connection is not defined uniquely. I will consider at least different connections. But now I start to consider contact sub-Riemannian manifolds. So theta will be fixed contact form. Theta is fixed. D kernel of theta contact distribution of codimension-one. So because theta is contact, D is non-integrable, and we have Reeb vector field Xi defined by those two conditions. So theta and Xi are fixed. Metric G is defined on D. Metric G is defined on D. I assume that dimension of the manifold is at least 5. Must be, of course, odd, because it is a contact manifold. And one of the properties of this Schouten tensor is that when we substitute two vectors, usually on a Riemannian manifold, we will have skew-symmetric transformation of the tangent space. But now this Cauchy endomorphism is not skew-symmetric. There is also symmetric part obtained given by the Lie derivative of the metric G. Generally, it's not must not be zero. So this is unusual property of the Schouten curvature. We compare it with the Riemannian curvature. Next, extended connections in this case. So of course, we have this vector field Xi. We have metric, so we obtain Schouten connection or horizontal connection. It will be always denoted by nabla, and any extended connection in this situation is given by some field of endomorphisms of D and maps sections of D to sections of D, and this extension, we need to extend the connection only in the direction of Xi. So it is given like that. And this extension is metric. It also preserves connection. if we don't leave symmetric part of this n equals to 1/2 of the Lie derivative of G, under obvious identification, because this is a bilinear form, but corresponding symmetric endomorphism. So skew-symmetric part of n may be chosen in arbitrary way. And this is formulas for the curvature of the extended connection, of arbitrary extended connection. Here R is a Schouten curvature, and so here we have values on xy when xy are tangent to D, and on xi x. These formulas are given like that. R nabla, Rn, so this connection nabla n is usual connection in the vector bundle D, and this is a curvature of this connection. This relation. Now there are two special extended connections. First connection is called usually adapted connection. N is symmetric given by this formula, and by the way, in CR geometry, this adapted connection coincides with the Tanaka-Webster connection. And another connection is Wagner connection. Wagner connection, this map defining the extended connection N, it is obtained if we substitute to R to the Schouten tensor the inverse of d theta. And this connection has in particular such property. And some references. So original works of Schouten 1 compound was the connection defined and the Schouten curvature defined. Now this work by Wagner, where he introduced the above connection, it was in 1937, and for this work he got a Lobachevsky Prize, and another Lobachevsky Prize the same year got Le Cartan. And in particular, the above connection was introduced in this paper, and motivation was the following. As I told, the vanishing of the curvature of Schouten connection is generally not equivalent to the flatness of the Schouten connection, and the flatness of the Schouten connection is equivalent to the vanishing of the curvature of that extended connection. This was motivation. Of course, this was done in arbitrary codimension, more or less for arbitrary distribution, not necessary for the contact distribution that I now consider. And so this is relatively old work now, written in language of classical differential geometry. There is some modern exposition of those results by Wagner, of this construction of the connection and of the Wagner tensor. And let me also mention a paper by my father, who was very enthusiastic working in that topic. And let me also mention that Wagner, he was advisor of my first supervisor, Miles Klosik, and he worked at the university the same as my father where I studied. And in fact, this problem to consider such things was suggested to me by my father quite many years ago. So I started, unfortunately, quite late. Now, some references on holonomy of sub-Riemannian manifolds. For the first time, holonomy of such connections were considered in the contact sub-Riemannian situation by Paul Gorodsky Rumin, 1997. Then there are more general papers where one considers arbitrary distribution of arbitrary codimension. That work, and let me mention also work by Philip Leitner, who studied parallel spinors on such CR manifold, pseudo-Hermitian manifolds. This is recent work. Now, let me state some theorems from those two papers. The first theorem it is some Ambrose-Zinger type theorem for the holonomy algebra of the horizontal connection nabla. It's similar to the usual Ambrose-Zinger theorem, but so we should to obtain this algebra, one point x is fixed. Then one consider all possible curves started in the point x. In this case, horizontal curves. Consider parallel transport, and here is the Schouten curvature. But now we are not allowed to substitute arbitrary vectors. It is allowed only to substitute bivectors alpha, such that d theta of alpha is 0. This is the main difference with the usual Ambrose-Zinger theorem, and this is another theorem. Just instead of this Schouten curvature, we may consider Wagner curvature and substitute then arbitrary vectors, because when we substitute such alpha, when d theta of alpha is non-zero, then RW is 0 on such bivector. And another general theorem. So suppose that we have some extended connection nabla n, and suppose that there is some bivector alpha such that curvature of alpha is 0. Then holonomy of the horizontal connection is the same as the holonomy of this extended connection. And in particular, this shows that holonomy group of the adapted connection coincides, of this Schouten connection coincides with the holonomy group of the Wagner connection. Now I will consider only K-contact sub-Riemannian manifolds. It means that Lie derivative of G is 0. So then adapted connection is given by those expressions, and in particular the curvature of the adapted connection is almost the same as the curvature of the Schouten connection, just this term, additional term, is 0. So, and for the Wagner connection, we have a little bit more complicated expressions, but this connection is important because its holonomy is the same as the horizontal holonomy. Now, I will assume that vector field Xi, the Reeb vector field, is complete. And let me denote its flow by phi t. Phi t will be the flow. Now x is a fixed point, and t0 in the case the orbit of the point x is cyclic. So t0 is the time when we first return to the point x. T0 is the smallest. But if orbit is not cyclic, t0 is assumed to be 0. This is notation. So in what follows, I assume that Xi is complete, but just let me remark that now there is, it is already proved that all those facts are true for arbitrary Xi, but this is not published, this extended results. So we have, I will consider Schouten connection or horizontal connection nabla. I will consider adapted connection. In this case, we consider parallel transport only along horizontal curves, only along curves that are tangent to the distribution. And here we have parallel transports along all curves, along all loops at the point x. So, of course, this group contains the first group, and the aim is to study both those holonomy groups. So now I state my results. So as I told, in one case we have all possible loops, in another case we have only horizontal loops. Now I consider arbitrary curve, piecewise smooth curve, gamma in M, and I construct, using it, I construct horizontal curve. So I consider such integral if gamma is horizontal, then theta of gamma dot is 0, so this integral will be constantly 0 for each t. So this integral shows some deviation of curve gamma from the horizontal distribution. And if we apply the flow of the vector field psi to this curve, no, there is minus, so in the inverse direction, here we have gamma, those are integral curves of psi, and it is necessary to move on such value the points of gamma. We obtain new curve gamma tilde, and this new curve is already horizontal. Gamma tilde is horizontal curve associated to gamma. Next, what is going on with the parallel transport? Suppose that xt, it is a vector field along gamma, which is parallel with respect to the adapted connection, because gamma is not a horizontal curve. Now, again, apply the flow of psi and obtain vector field along gamma tilde. And next result is that if x is parallel along gamma, then x tilde is parallel along gamma tilde. No, this is because generally, because I assume that manifold is K-contact. So G is constant along psi, and in particular psi preserves the connection. So this is the reason. So here we have parallel results of the parallel transports. But it's important to note that the endpoints of gamma and gamma tilde must not be the same. So we get two parallel transports, and results are at different points. Now, if we assume that gamma, this arbitrary curve, and the associated horizontal curve, if they have the same endpoint, then parallel transport along gamma for the adapted connection is the same as the parallel transport along gamma tilde for the horizontal connection. So we get such relation. But here I assume that the endpoint of gamma tilde are the same. So now, suppose we have a loop, gamma is a loop at the point x, and then curve gamma tilde is also a loop at the point x. If we don't leave, this integral belongs to the t0. T0 is this number related defined above for the case the orbit is cyclic, and if orbit is not cyclic, this is just 0. The proof to see the endpoint of gamma tilde equals to phi fb. So this is flow of psi applied to this point gamma b, and this number fb is just minus that integral. And now tilde gamma of b equals to gamma b. If we don't leave, this number belongs to the t by the definition of t0. So now we may state that an element of the adapted holonomy belongs to the horizontal holonomy. If we don't leave, this element h might be represented by a loop gamma satisfying this condition. So horizontal holonomy consists of h from the adapted holonomy such that there exists gamma even h. So this is characterization of the group inside. And now next result is that this horizontal holonomy is a normal. It is a normal Lie subgroup of the adapted holonomy. Let's explain again the proof. Mu, let mu be a horizontal loop at the point x, and gamma arbitrary loop at the point x. Then we consider such a loop, and integral along theta is 0, of course, because we go along gamma and then along gamma -1. Integral along mu is 0 because mu is horizontal. And then when we consider this expression, it is parallel transport along this curve, and we know from the above that this parallel transport, because integral is 0, belongs to the horizontal holonomy. So we have element tau mu from the horizontal holonomy and the element tau 0 gamma element from the adapted holonomy. Consider such element and we obtain element here. So this subgroup is normal. And even more, there are only two possibilities. Either the groups are the same, horizontal holonomy is the same as the adapted holonomy, or this horizontal holonomy is a normal subgroup of codimension-one. Only two possibilities. Here's the proof. It's just not hard to construct surjective homomorphism from R plus to this quotient. So since we have this, it is connected, it's clear then either this quotient is trivial or it is one-dimensional. So we get this result. Next result, it states that this adapted holonomy is just the holonomy algebra of the Levi-Civita of some Riemannian manifold, So it belongs to the list that I give at the beginning. It's easy to prove because, as I told, the curvature of this connection is given by the Schouten curvature. The Schouten curvature satisfies the Bianchi identity. Then we use the usual Ambros-Zwingli theorem and see that this holonomy, it is so-called Berger algebra. It is spanned by images of algebraic curvature tensors. And each Berger algebra, it is known that each Berger algebra is a holonomy algebra of some Riemannian manifold. So this Riemannian manifold, which is associated to this algebra, is not somehow constructed directly, just using the classification language of Berger algebras. I show that this should be holonomy of some Riemannian manifold, and it is important, then it is known. This holonomy algebra is known at the very beginning. I gave list of corresponding groups, of the corresponding connected groups. Now, from the theorem decomposition, as I told, the holonomy of arbitrary manifold, Riemannian manifold, it is direct sum, in this case algebras, of irreducible HI. So the space dx may be decomposed as such direct sum, orthogonal direct sum. Holonomy algebra also decomposes. So D0, this is subspace annihilated by the holonomy algebra, and each HI X in Di irreducibly, and this is again Riemannian holonomy algebra. So this is description of those adapted holonomies. And a remark, so we have fixed Reeb vector field psi. It defines one-dimensional foliation. It's called a characteristic foliation. And the normal bundle of this foliation is this quotient. And then this normal bundle may be identified with the distribution D. D is the normal bundle to the characteristic foliation. And this condition that space is K-contact, it means that G is a transverse Riemannian metric on the foliation F. And also in that case, connection, adapted connection is just the same as transversal Levi-Civita connection of this Riemannian foliation. Because I will use this terminology in some statements. So now, okay, so we have two possibilities. Either horizontal holonomy coincides with the adapted holonomy, or horizontal holonomy is of codimension-one. And now this theorem describes the second possibility, probably the most interesting case when those two holonomy algebras are different. And here we have equivalent condition. So first condition that horizontal holonomy algebra is of codimension-one subalgebra of the adapted Holonomy algebra. This is horizontal, this is adapted. And equivalent condition is the following, so that the adapted Holonomy algebra is contained in UM, in the unitary algebra, and it means that this Riemannian foliation F admits transverse scalar structure G. Next condition is that D0 is trivial, so there are non-zero vectors annihilated by the holonomy, and each HI in the decomposition into irreducible parts must be contained in the corresponding unitary algebra, and it must contain the corresponding complex structure U1, corresponding U1. It cannot be contained in SU. It must contain U1. And additionally, d theta, there should exist some number B1 so that d theta satisfies this equation. Rho, what are those rho? Each of the distributions di, they have some Kähler structure, and rho I are corresponding Kähler forms. So Ricci tensors multiplied by G, so they're skew symmetric. No, Ricci forms, they're Ricci forms, sorry, Ricci forms. In fact, we have this decomposition di, and complement to each of this distribution is integrable distribution, and it again gives foliation, and corresponding di is a normal bundle to this foliation. So we have some number of foliations with scalar transverse structure if this condition is satisfied. So just
can something be said in the situation when you don't have this simply connectedness condition?
No, I'm speaking here about holonomy algebras. So this would be true on some open subset or on some simply connected neighborhood of the points that we consider.
Okay, so locally, it could be described locally. That's what you're saying, right? I see. Okay.
Yes. Or sure. Otherwise, it's necessary probably to have here the condition that holonomy group is normal codimension-one subgroup of that group. In this situation.
Thank you. Yes, thanks a lot.
Why this scalar structure appears? Because holonomy algebra is in this unitary algebra, but it's not enough. We need the condition to get global. If manifold is not simply connected, then holonomy group is different from, is not connected. Holonomy group is not connected, and simply this holonomy algebra does not control everything. If there is a standard fact that there is a parallel object. I mean, I speak now about this complex structure. If and only if at some point the corresponding value is preserved by the holonomy group. But here we have only weaker conditions that only holonomy algebra preserves this. And when manifold is simply connected, then holonomy group is connected. And then this holonomy algebra defines this uniquely. This is the reason why such assumption. I speak about holonomy algebras now, so I may assume that manifold.
Yeah, thanks a lot. Thanks a lot.
Thank you. And just one remark, in fact, important remark, that this Kähler structure is not unique, is not defined uniquely. J. If there are more factors, R factors, then there are so many 2 to the power R parallel transverse Kähler structures, because we may restrict it, this, when we have one parallel Kähler structure, we restrict it to the components D1 and so on, dr, and we change the sign. This would be another structure. In particular, I will speak about Sasaki manifolds later. For the Sasaki manifold, there is a canonical Kähler structure. And the Kähler structure here, which appears here, it must not coincide with the canonical Kähler structure on the Sasaki manifold. The canonical Kähler structure would be somehow related to this. This will be important when I speak about parallel spinors later, if I have time. And now this is a description of the horizontal holonomy algebras in the case of codimension-one ideals of the adapted holonomy. If those two holonomy algebra coincide, then they are known because they are Riemannian holonomy. Interesting case when they are different. So recall that above we had such decomposition for that adapted holonomy, and then this horizontal holonomy, it is of codimension-one ideal here. So semi-simple part must be the same. H prime, H1, it is contained in the unitary algebra. It has semi-simple part and one-dimensional ideal, commutative ideal, one-dimensional radical. It is given by the complex structure. So this horizontal holonomy contains the same semi-simple part and its commutative part, just codimension subspace of the commutative part of that holonomy. It can be described as an orthogonal complement to some one-dimensional subspace Tx. By the way, these numbers A1, AR may be considered as the same as B before. So now, in fact, this is classification. Let me show examples. What may happen? So, for example, there are two factors. Dx is direct sum of dx1, dx2. Adapted holonomy is direct sum of um1, um2. Such to Kähler, so in matrix forms, you see this is completely reducible. It preserves the decomposition and splits into two parts. And now codimension-one ideal here have such form: H prime 1, H prime 2, so SUM1 plus SMU2 plus some one-dimensional subspace of the space generated by G1 by G2. So it has such matrix form. So you see that we have here some diagonal part. And by the way, alpha beta must be different from 0. So in this case, this horizontal holonomy, it's not Riemannian holonomy. It cannot be a holonomy of some Riemannian manifold because of this part. Usually, by the Dirac decomposition theorem, Riemannian holonomy splits into two parts, like here, if it is not irreducible. And another series of examples suppose that so this adapted holonomy is irreducible, and it is holonomy of some Kähler space. So it is either UM or it is a holonomy of Kähler symmetric space, or so-called Hermitian symmetric space, and then it is in the list. And the then the horizontal holonomy may be the semi-simple part of them, and none of those semi-simple parts except for that case when H prime is SUM, none of them are Riemannian holonomy algebra. So this horizontal holonomy algebra is almost never Riemannian holonomy. This classification is somehow different from the G classification of Riemannian holonomies. And here another example, such holonomy SOM plus U1. It is contained in UM. So SOM is embedded. SOM is embedded in UM in this way. And additionally, there is this commutative part, one-dimensional. It is generated by the complex structure. So this holonomy is irreducible in UM. It is holonomy of symmetric space SOM plus 2 by SOM times U1. This holonomy of symmetric space, and then the corresponding horizontal holonomy may be of this form. It's not irreducible anymore. This was irreducible because of this part. This algebra is not irreducible anymore. Again, it's not Riemannian holonomy. This is typical examples. The general situation looks like that. And no, why call this? This is when it is irreducible. This part irreducible, so there is only one t in the decomposition above d1, and this case when there are two. And construction, all those cases considered in the theorem, then they can be realized. They can be realized. Here's a construction. No, in fact, this is I consider it in this way, but we simply consider some number of Kähler manifolds with irreducible holonomy, rho I corresponding Ricci forms, and we assume that they are also exact. But in fact, what I consider is the canonical S1 bundle of the over-Kähler manifold. In this canonical S1 bundle, it admits canonical contact structure. And this is some simplification for understand. So manifold M is the product of R with M1 and so on, MR. Theta contact form is denoted, defined as d theta plus some combination of those forms ti that I assume exist. And then di corresponding distributions in the above. So, we get a sub-Riemannian metric. It corresponds because each ti may be identified with a TMI. We get corresponding metrics, and it's in this case everything is just as above theorem. When we have situations that the horizontal holonomy is different from the adapted holonomy. Adapted holonomy may be identified with the product of this holonomias, and the horizontal holonomies of codimension-one. Yeah. Special case of so-called Sasaki manifolds. Here's a general definition. It is Sasaki manifold is a Riemannian manifold with a special Killing vector field Xi, which satisfies some conditions. But let me give another interpretation. Suppose that we again have a K-contact sub-Riemannian manifold, extend the sub-Riemannian metric G to metric H on M, Riemannian metric M, and this is relation of the corresponding Levi-Civita connection and the horizontal connection nabla. Xi, it is symmetric endomorphism defined by d theta. And now characterization of the Sasaki structure in terms of the Schouten connection. So when we have a K-contact sub-Riemannian manifold with a Reeb vector field Xi, then corresponding manifold M Xi H like here is Sasaki. If and only if Xi given by this, it is complex structure on D, and it is parallel with the Schouten connection. And as a corollary, suppose that we have a Sasaki manifold, then this condition holds true if and only if the transverse scalar structure of each foliation Fi is Einstein and not Ricci flat. So we have this equivalent condition. I told that Fi is a foliation such that its normal bundle is di from the above. Di. So such characterization of this inequality in the case of Sasaki manifolds. And as application, obtain result for manifolds, K-contact manifolds that admit parallel horizontal spinor. At the beginning, I gave a list of holonomias of Riemannian manifolds that admit parallel spinor field. In the irreducible case, there are only 4 possibilities. G2 spin 7 SU K SPK. Let's see what's going on here in this K-contact case. So we have, so suppose that we have simply connected sub-Riemannian manifold, and PSO will denote the bundle of positively oriented frames on D, only on D, not on the manifold. And spin structure in this, then, or maybe to say horizontal spin structure, is a reduction of this bundle to some other principal bundle with a structure group spin 2M. So this is some generalization of the standard definition when one consider 10 bundle of all orthogonal frames. And then if such structure is fixed, then one considers spinor bundle as, so it is associated vector bundle, and its fiber are standard spin modulus, spin representation of the spin group. And connection nabla is then extended to connection on spinors. But again, this is horizontal connection, because we may consider covariant derivative of spinor field, but only in the horizontal direction. And Holonomy algebra of this connection is just the Holonomy algebra of the horizontal connection, but with its natural representation in the spinor model. And by the standard principle, we have a parallel spinor S, if and only if there exists spinor annihilated by the Holonomy algebra. It's element of the spinor model. So, and now the result. So when we have simply connected the K-contact sub-Riemannian manifold with fixed spin structure, complete Reeb vector field, but not necessary to assume that. And if those Holonomy algebra are different, then there exists non-zero parallel spinor if and only if there exists a transverse scalar structure J, such that Holonomy algebra is contained in SU dx, gx, jx with respect to this transverse scalar structure.
Anton, could you please say why do you assume that the dimension is high enough? Why it's supposed to be greater or equal than 5?
Dimension 3, no, I don't consider dimension 3. I don't know, there should be something trivial in this dimension. Because there are not so many possibilities when we study Holonomy algebra, then it would be contained in SO2. So it would be either trivial, the Holonomy algebra, or it will be SO2.
I see. Thank you.
So I wait. So should be in SU, and it is important that this SU special unitary algebra contained here, it is defined by this complex structure Gx. And when we consider another parallel, another Kähler structure, then a holonomy would not be contained in SU with respect to another structure. So this is important here, that there exists, in the condition that there exists some parallel Kähler structure such that holonomy algebra is contained in SU with respect to this structure, because we may start with the Satake manifold, then there is canonical transverse Kähler structure, and holonomy must not be contained in U, in SU with respect to that canonical Sasaki Kähler structure. So the remark and how to get this, as I told, we just need to find those holonomous algebra that in the representation here has non-trivial element. And here standard decomposition of the spinor model with respect to UM. The algebra UM, it has such decomposition. In each factor, we have standard representation of SUM, and the complex structure J acts here as multiplication by such number. So you see, by this, because of this, for example, UM doesn't annihilate any non-zero element. By SUM, it annihilates elements of lambda 0 and lambda m. And okay, in the above classification, we considered arbitrary decomposition of D into reducible parts. Then the spinor modulus, then it is tensor product of the corresponding spinor modulus, and then we have such decomposition. And important lemma that I prove that when we have holonomy algebra of irreducible Kähler symmetric space, then this semi-simple part H prime does not annihilate any non-zero element here when K is different from 0 and from n. So semi-simple part of H, not of this H, but of our horizontal holonomy, if it annihilates something, then corresponding Ki must be either 0 or it is Mi, which corresponds to the dimension of the corresponding deltas. So when we and note also that this decomposition depends on the choice of the complex structure on C to M Jx. So we might, when we change the complex structure, we get that either all those chi I0, all of them corresponds to the rank Mi. So space, if the space of parallel spinors is non-trivial, then it is two-dimensional in this case. No, in fact, this is all. This was application, and just let me announce then a continuation of this work that will appear next days. It is, I will not announce results. You will see on archive very soon that there's some continuation of this work written together with Thomas Leisner and Philipp Leitner. It will appear next days. So this is all. Thank you.
So thank you very much, Anton. Yes. That is a very interesting talk, in the continuation. It seems very promising. Roman, do you have any questions?
Not really. Thanks a lot. Oh, maybe like what will appear in the continuation? What type of results?
You will see in
okay,
in a few days. You will see.
Okay, sure. Yeah.
Okay, so that means that you should give a talk next semester, right? Maybe
yes, it's possible. Yes. At least what is done there, it is proof that all those results I told them. I had this assumption that Xi is a complete vector field. What is proved there that Xi must not be complete.
Yes.
But
so,
there are many more results. I like 35 pages, so quite a big paper.
Oh, quite long. So of course you want to keep secret to the last minute, because sometimes the better reason is in the last minute, right? And
you will see. Yes.
Yeah, and so I see that's how to say that is you say that K-contact sub-Riemann manifold, but many people say just the contact metric manifold, right? Because of different terminology.
Yes. I don't know. Maybe something with integrability or almost contact. Yeah,
because contact is never integrable. By definition, it's a maximum.
Yes, but no. I mean integrability or something. Yes. Sometimes we will say about almost contact metric manifolds. Then additionally, there is this skew symmetric, like here, this Xi, and this should be either integrable or not, and so on. It's somehow was. I think that this is more easier settings to understand that we have contact distribution, fixed contact structure, contact distribution, and metric on it.
Yes, but then we cannot, how to say, even on this metric homotopic, we cannot find any invariant, right, for contact structure.
Invariance of
because such a you consider that, how to say, that's I think that the Roman had interest because of course not only because it's interesting, but my thing, can we apply some idea from here for contact geometry or not? But not so clear.
No, yes, probably there could be no, I'm not quite familiar with those things, because in the Riemannian situation, there is some different relation to the topology. You know it better. Some, when we have holonomy spin 7, for example, in the Riemannian setting, some topological restrictions on the manifold and so on. I'm not so good familiar with that, and in particular, in the Keller case, some relation to the cohomology called of Keller manifolds and so on. I'm not. Maybe there could be also some similar relation, with some restriction on the topology on manifold if you have this, some assumption on the not on the holonomy algebra, but on the holonomy group, when it is say SU, the holonomy group SU, SUM. Probably there's something about that, which I'm not quite familiar.
So
in the
that's a really special geometry. Yes.
Yes, there should be results like this. Yes.
I think in general, even like if one considers, let's say, Sassakian manifolds, then there is at least a restriction on fundamental group, and there are like people who study this type of restrictions. Let's say Hradec-Králové studies this type of questions, like what type of fundamental groups can be realized as the fundamental groups of Sassakian manifolds. So there are some topological restrictions in this case. Yeah.
Yes. And if we make some assumption of the holonomy group, then there will be some more restrictions.
Right.
There are such results in the case of Riemannian, just Riemannian.
Sure. Yeah. Thanks a lot.
So if there are no more questions, let us thank the speaker again.
Thank you very much.